Okay, so welcome back. The plan for today is to work through sections 8.2 and 8.3 on continuing with our discussion of rational expressions, continuing with operations on them, and looking at multiplying, dividing, and addition, and adding and subtracting rational expressions. We do have Unit 2 exam this week, so if you haven't already, I would recommend completing that exam in the near future. Make sure to leave yourself a little bit of buffer before the due date that's this Sunday. It's available on the website, and the sample exam is available. Essentially the same parameters apply to the Unit 2 exam as for the Unit 1 exam. This coming week, we have just wrapping up our Chapter 8 material, just wrapping up the rational expressions material, and then we're already into finals week. So our final exam will open up Friday the 2nd and be available through Friday the 9th at 11:59 p.m. Again, I'll post a little more information about that next week once we have Unit 2 exam wrapped up. But we're starting a little bit before the official final exam week. And the reason is that I know with remote classes, folks tend to take these for logistical reasons, and this gives you a full weekend to take the exam if you want to do that. So it will be open a little bit before the official final exam week to take advantage of that weekend. But of course, you can definitely wait until the proper final exam week to take it if that works better for you. Okay, and the quote of the day, or two quotes of the day. This is, I think, a really interesting debate in mathematics and maybe even outside of mathematics and philosophy. So there's one quote by Leopold Kronecker, a famous mathematician, physicist, where he says, God created the integers, everything else is the work of man. Essentially, his argument is mathematics is a human creation. It's something like, if somebody goes and draws a painting, that person created that painting. I guess you don't draw a painting. If you paint a painting or draw a picture, if you draw a painting, that would maybe be be something else. But Kronecker is saying that essentially mathematics is created by man, by human beings. Eugene Wigner, or I'm not exactly sure how to say his last name the correct way, so I'm going to Americanize it. Eugene Wigner has a famous paper that's just titled The Unreasonable Effectiveness of Mathematics in the Natural Sciences. And essentially his argument is that there is evident an unreasonable effectiveness of mathematics in the natural sciences. So maybe we see something that we're interested in nature and we want to describe it. We come up with a mathematical model to describe it. Okay, I mean, maybe we created that mathematical model so that it matches the thing we're looking at. But then the unreasonable part is, well, then we find something in nature that's adjacent to the thing we were looking at, and our model still kind of works for that too. You wouldn't expect that to work, right? If I just tailored my model to the thing that I knew about, I'd expect that when I discover something else, I need to back up and make a new model that fits both of these, these two things that I know about now in the natural world. But his argument is the effectiveness of mathematics in describing nature is unreasonably effective. So it's not just that, we're creating things to do the job that we want, or we're creating tools in our toolbox to solve specific problems, but that, it would be like if I created a screwdriver to screw in a screw, but it also worked just as well to hammer a nail or, saw a board in half or something like that. And that's really this debate, mathematical formalism. Do humans create mathematics? Is it just a human invention? Or mathematical Platonism, named after Plato, the Greek philosopher, is essentially mathematics somehow inherently embedded in nature to some extent, and we're effectively discovering mathematics. Or I think another way to phrase it is, think about, say, like the game of chess versus gravity, right? Like gravity that pulls on us, right? So if you think of the game of chess, I mean, I think everybody would agree that that chess is a human invention. I don't think anybody would argue that, you know, chess was sitting out there in nature waiting to be discovered. The rules of chess were waiting to be discovered by us or something like that. Maybe somebody would, but I haven't heard that argument yet. Um, but somebody came around and said, okay, this we'll call this piece a pawn and it'll move this way, and this piece is a bishop, it'll start here and move this way, and so on. And as a result of that, somebody set these rules, but surely they didn't understand the entirety of the game, right? They didn't understand that you can checkmate a king with, say, a bishop and knight. It's kind of a hard, you know, painful process, but it's doable. But you cannot checkmate a king with just two knights and your king, maybe unless your opponent cooperates very nicely. So they might not have understood the full extent of the rules that they set out, but you know that they made some choices, some axiomatic system, we might call it in math, and then we can discover interesting things about conclusions of those that system versus something like the law of gravity. The law of gravity is going to work the way it works, whether you know about it or not, whether you like it or not, whether you want to change it or not, or even whether you understand it or not, right? Gravity is going to pull you down to the earth the same way that it would if you know, are a 2-day-old kid that has no understanding of math or anything like that, or, you know, a PhD in physics. So the law of gravity works the same. Uh, so we can discover things about it. You know, which side of the coin does math fall on? Is math discovered or invented? So I'm pretty firmly in the mathematical formalism side. I think that it's in essence completely a human invention made because it's very useful in understanding the world around us. Um, but there are a lot of people much smarter than me that fall on the side of mathematical Platonism. So I don't think it's a solved problem at all. But I think it's just an interesting thing to think about when we talk about mathematics, or for that matter, when you take this material and you apply it to whatever natural science you're working with, whether it's physics or chemistry or, you know, even things like biology or nursing, or um, you know, to what extent are these structures that we're dealing with in those other sciences uh, human invention versus inherent to the real world. Okay, so moving on to 8.2. So we're looking at multiplying and dividing rational expressions. And we remember that in some loose manner of speaking, the simplest rational expression we can deal with is just a ratio of two integers, 1/2 or 2/3 or something like that. And I mean, that's kind of technically a monomial over a monomial, just the degree zero monomial divided by a degree zero monomial. So let's look at an example. So let's take 3/2 times 12/3. Sorry, my allergies once again are annoying me this morning. Uh, so if I take 3/2 times 12/3, I might remember that I have a fraction rule that a over b times c over d. When I'm multiplying two fractions, I multiply the numerators and I multiply the denominators. My new numerator is a times c, my new denominator is b times d. Okay, so I look at 3/2 times 12/3. I can multiply these together as 3 times 12 divided by 2 times 3. And at this point, I have one fraction. I could multiply my numerator, multiply my denominator, get 36 over 6. But I also want to simplify my fraction. I always, by kind of default, want to write my answer in simplest form. So I'm actually going to leave it factored. And I might even notice that I have a common factor already. The 3's can divide out. And I might also notice I can write 12 as, say, 3 times 4 or 3 times 2 times 2 over the 2 that remains in the denominator. And I look at this and I have another common factor that I can divide out. And we could either think of this as being like 2 times 1 in the denominator, or 3 times 2 is just 6. 6 over 1 is just 6. We want to be a little bit careful. We don't want to like divide out the 2's and then write like 6 over 0 or something like that, thinking that we like have a 0 in the denominator. That, of course, wouldn't be correct. But so it's 6 over 1 or 6. Or if we're thinking about dividing the fractions, if I have, say, 1/4 divided by 3/2, so remember, if I have a over b divided by c over d, this is a over b times d over c. So I take my fraction that's being divided by the second one, I invert it, and I multiply. Or that's going to be a times d over b times c. So this is 1/4 times the 3/2 gets inverted to 2/3 and multiplied. And now I multiply across the top. I get 1 times 2. Across the bottom, 4 times 3. And it's a little easy to do this in our head, but I'm going to be a little more pedantic about it, because when we get to rational expressions, of course, we can't see these factors nearly as easily when we get to proper rational expressions. So I have 1 times 2 on top. That's already, I guess I don't need the 1 there necessarily, just 2 on top. That's already prime. But 4 can be broken down into 2 times, and then the 3. My 2's divide out, and then I can combine things back together to get 1/6. And one little side note is I could have actually made my life a little bit easier in the first problem if I had noticed the 12 over 3. Actually, that fraction can be simplified even before I do the calculation. So 12 over 3 I might recognize as 3 times 4. 4 over 3. These 3's can divide out. 12 over 3 is just 4. So I would get just 3/2 times 4, or that's 12 over 2. And I can see that there's a factor of 2 that comes out of the 12. 2 times 6 over 2 is 6. So when I'm dealing with rational expressions, or with the operations on rational expressions, it is often useful for me to kind of at each step along the way simplify as much as possible. Okay, let's look at an example. So let's try to simplify this product of 2 rational expressions. So we're multiplying 5x squared over x squared minus 2x minus 24, multiplying that by x squared minus 16 over 15x. So I think the first thing that I'll do is I'll take these quadratics and try to factor them. The 5x squared is just a monomial. It just is what it is. X squared minus 2x minus 24, does that factor? Well, I think maybe x minus 6 times x plus 4. Negative 6 times positive 4 gives me negative 24. Negative 6 plus positive 4 gives me negative 2. So I think this is x minus 6, x plus 4, that it factors into. I'm multiplying that by my second rational expression. The 15x in the denominator, again, a monomial, nothing we can do with that. But the numerator, x squared minus 16, that's a difference of 2 squares. That factors into x minus 4 times x plus 4. Okay. Now, one thing that I really probably want to do here, I'll typically skip over this step when we're focusing more on multiplying, dividing, adding, subtracting rational expressions. But something that we really ought to do is write our restricted values. Now the things are factored, I can see what's not allowed to be plugged in. X cannot be, well, x minus 6 in the denominator, x cannot be 6. X plus 4 is in the denominator, x cannot be negative 4. And 15x is in the denominator, x cannot be 0. So before I start doing operations on my rational expressions, and certainly before I start simplifying things, I want to make note of my restricted values. Okay, now, do I have anything that divides out? In my first fraction, no. In my second fraction, no. Doesn't happen to have, I don't happen to have anything that simplifies nicely here. Let's do one step then to combine these together. I can multiply across the numerator and multiply across the denominator. I'm going to put this 15x out in the front. And then I have x minus 6 times x plus 4 in the denominator. Okay, and now I can start looking for common factors between the numerator and denominator. I see there's a factor of x plus 4. I have x plus 4 multiplied by a bunch of other stuff in both the numerator and denominator. Again, very important that I have that whole x plus 4 kind of separated off and it's multiplied by everything else. If I had like x plus 4 plus a bunch of other stuff, I wouldn't be able to divide that out this way. Because it's multiplied, I can divide that out. I see with the 5 over 15, these are just numerical factors. I can see pretty easily the factor of 5 divides out, leaves me with a factor of 3 in the denominator. The x minus 4 and the x minus 6, those don't have any other common factors to divide out with. But the x squared and the x, I can actually get rid of one of the factors of x. So I can get rid of this whole x, and I'll kind of just cross off the power there, indicating that we've gotten rid of the one factor of x, but the second factor of x does remain. So what am I left with? And as an aside, you can definitely do this in 2 or 3 steps. If you want to, to write it out a little more explicitly, that's perfectly okay. So what am I left with? In the top, I have x times x minus 4. And in the denominator, I have 3 times x minus 6. And notice we still do kind of implicitly have the restricted value x can't be 6. We see that in the x minus 6 in the bottom. But we no longer implicitly see that x cannot be negative 4 or 0 because those bits were divided out. So that's why technically we got to be careful and write the restricted values all out. Sometimes I will, sometimes I'll gloss over that in order to allow us to focus on the task at hand. Okay, let's jump right into an exercise then. So simplify this product of 2 rational expressions. The first is y squared plus 3y all over y squared minus 3y minus 4. And the second is y minus 4 over y squared. Those are multiplied together. So simplify that product. Let's take maybe about 3 minutes or so, work through this one, and then come back and discuss it. Okay, it's just about 3 minutes, so let's take a look at this one. So the first thing we'll do is we'll factor each of the numerators and denominators. The second rational expression doesn't really need factoring at all, but the first, both numerator and denominator, we can factor. We can factor a greatest common factor of y out of y squared plus 3y, giving us y times y plus 3. And the denominator, y squared minus 3y minus 4, factors into y minus 4 times y plus 1. As a little side note, a little bit of kind of test-taking strategy. If you see a rational expression problem, um, it's fairly often that something's going to end up simplifying or dividing out. So if I see that there's a y minus 4 in the numerator over here and that this is getting multiplied, I'm kind of thinking to myself, I wonder if there's a y minus 4 in the denominator. Or maybe I'm thinking to myself, I wonder if there's a y plus 3 in the denominator. So that can actually give me a hint on maybe how some of the numerator or denominators might factor. I'm thinking to myself, I wonder if there's a y minus 4. That gives me something to go off of here. Now, that might not turn out to be true, that we might not have anything to divide out, or maybe the y minus 4 just doesn't divide out. But that can be a strategy to help save a little bit of time or effort. Okay, so we factored everything into y times y plus 3 over y minus 4 times y plus 1, multiplied by y minus 4 over y squared. Again, I can look at my restricted values here. Y cannot be 4, -1, or 0, or I would get a 0 in the denominator. And I don't want that. And one thing that I did here is I added grouping symbols around my y minus 4. I don't want to get to my next step and one that's not wanting to let me select just that parentheses, but I don't want to get to my next step and have something like this, right? Y times y plus 3, and then what looks like multiplied by y, all of that, and then subtract 4. That would not be correct, right? I'm multiplying the entire first numerator against the entire second numerator, y minus 4. So I do need these grouping symbols, these parentheses in there. Okay, so I multiply everything together, multiply the tops, multiply the bottoms. I rearrange things a little bit in the denominator to get my common factors lined up a little nicer. And I look for things that divide out. I see I have a factor of y minus 4 on the top and bottom that can divide out. I have a factor of y on the top and bottom. The numerator, the y factor, divides out completely. And the denominator, I have y squared. So I have two factors of y. I lose one of them with the dividing out and keep the other one. And then all that I have left on top is y plus 3. So I guess it wouldn't be wrong to keep that in parentheses, but it's kind of more standard to take the parentheses away because they're no longer needed. In the denominator, I have one factor of y left times the y plus 1. Okay, now what about division? So here I have one rational expression divided by another. I know that sometimes the division sign can look like a plus sign, especially if you're on a smaller screen. So I try to be pretty clear when I'm explaining it, which one I'm talking about. But if you're on WebAssign or something like that, maybe zoom in a little bit and make sure whether this is a divided by sign or a plus sign. Okay, so I have a similar setup. I have rational expression divided by rational expression. And I think I'm going to do the same thing. I'm going to start by factoring everything. The 24x squared, nothing I can really do with that. 4x minus 16, I can factor a 4 out of there to get x minus 4 divided by 3x minus 24. I think that can be, I can factor a 3 out of there, and it can be factored into 3 times x minus 8. Then x squared minus 12x plus 32 Well, I know -4 times -8 gives me 32, gives me positive 32. -4 plus -8 is -12. Again, I might have gotten that inspiration from seeing the x minus 4 and the x minus 8 popping up here. And that does work. So what are my restricted values? I can't have this denominator being 0. I can't have this denominator being 0, but I also cannot have this entire second rational expression being 0. So my restricted values, x cannot be, we have a lot of repeated bits here, but the x minus 4 bit can't be 0, and that would happen if x was 4. And x minus 8 cannot be 0, both because it would make this denominator 0, but also because it would, in a sense, make the entire second fraction 0. And because we're dividing by the whole second fraction after this divided by symbol cannot be 0 either. So x can also not be 8. And those are my restricted values. Okay, now I want to start simplifying. I could take my second fraction, invert it, and multiply, and there's nothing wrong with that. But something I might notice is, hey, I actually can make things a little bit simpler right now. The second rational expression can actually be simplified. I can divide out the x minus 8s. So I have 24x squared over 4 times x minus 4. And I suppose I could also divide out these. 24 divided by 4 is 6, but I didn't do that, and I won't worry about that. Now here I'm dividing by a fraction, so I invert the fraction and multiply. That what's left is 3 divided by x minus 4. I invert to make x minus 4 divided by 3 and multiply. Now I multiply the numerators together. 24x squared times x minus 4, and multiply the denominators together. The 3 multiplies against the 4 to make it 12 times x minus 4. My x minus 4s go away, and 24 over 12 is simply 2. So I end up with just the monomial 2x squared coming out of this. Lots of cancellation here, just get 2x squared. And of course, that's subject to these domain restrictions. Okay, let's look at 2 exercises. We have one here that's one rational expression divided by another. We have a second exercise that's a bit more challenging. Actually, 3 rational expressions. A first one times a second divided by a third. This second example doesn't really work procedurally much differently than anything that we've done before. But give it a little bit of thought. How would you do this? Does order of operations really matter all that much? How might you approach this type of problem given, number one, what you know about how we approached the previous rational expression problems, but also number two, given what you know about how you can multiply and divide just numerical fractions. If you need a little bit of inspiration, think of like, what if you had 1/2 times 2/3 divided by 3/4? How would you approach that kind of a situation? Work that out, and then apply a similar process to this problem. That's a really powerful idea especially in mathematics, but in a lot of fields, is can you find a problem with a similar structure that's just much simpler, and you can see how it works, and then you can apply the same process, or at least try to apply the same process to the more complex problem. Sometimes it works, sometimes it doesn't. In this case, I think that would give you quite a bit to go on. If you're stuck with this problem, take 3 numerical fractions, 1 multiplied by a second divided by a third, ask yourself how you'd proceed through that, and then take a look at these rational expressions. Okay, so we'll take probably about 8 or 9 minutes for these because both of these are pretty big problems and a lot to do, factoring and so on. You're getting a lot of nice factoring practice here. So factoring and so on, and also handling the extra complexity here with 3 rational expressions being operated on. So we'll take 8 or 9 minutes and then come back and discuss. Okay, we're right at about 9 minutes, so let's talk about the answer to these two. So again, two lengthier problems. But I hope that each of the individual steps isn't, too challenging for you, but it's just a lot of individual steps that you have to link together the right way. This also gives a good bit of practice on some slightly more complicated factoring that we haven't really that we haven't run into since the break, I suppose. We've been focusing on the rational expressions bit, so trying to keep the factoring simple, but we had a couple of more complicated factoring examples here. So the first one, we want to simplify this quotient of two rational expressions. So we'll start by factoring 8x squared plus 15x minus 2. And coming over here, we see that using the AC grouping method, we're looking for two numbers, m and n, that multiply to be a times c, or negative 16, and then add to be the cross term of 15. And we can see just by inspection that that would be 16 and negative 1. 16 minus 1 gives me 15, and 16 times negative 1 gives me negative 16. So I split up that middle term as 15x equals 16x minus x, and I factor by grouping. So I end up with 8x minus 1 times x plus 2. My denominator, x squared minus 64, I recognize as the difference of two squares. So that's x minus 8 times x plus 8. For my second rational expression, before I do anything with flipping it or anything like that, I'm just going to focus on factoring first. 8x squared plus 63x minus 8. Coming over here to my blue scratch work. Again, using AC grouping, I see I'm looking for two numbers, m and n, that multiply to negative 64, 8 times negative 8, and then add to the middle term of plus 63, the coefficient of the middle term, 63. And again, I see that this isn't too hard to just intuitively find the answer, m equals 64, n equals negative 1. And we break that plus 63x into plus 64x minus x. And again, we factor by grouping. We get x plus 8 times 8x minus 1. And then my denominator here I recognize as a perfect square trinomial. It's going to be x plus 8 all squared. So this should go pretty quickly. I think I had completed this one at about the 5-minute mark. So, and I started after about 1 minute. So, you should have probably had this one done at about the same time, around the 5-minute mark, maybe the 6-minute mark. At this point, this factoring should be a pretty smooth process, right? Okay, so then I noticed that I have fraction divided by fraction. So the first thing maybe I'll do is write out my restricted values. I see that none of these factors are allowed to be 0. So x cannot be 8 or negative 8. But also this numerator cannot be 0 because we're dividing by this whole second fraction. And if the numerator were 0, that would make that fraction 0. So again, x cannot be negative 8, but we already had that. But also 8x minus 1 cannot be 0, or x cannot be 1/8, 1 over 8. That's another restricted value for x. So we want to be a little bit careful here with our restricted values. So I've got my restricted values. Now I put a little exclamation point on that 1/8 because it's an easy one to miss. Now we proceed with simplifying. We invert the second fraction and multiply. So we have first rational expression times x plus 8 all squared over x plus 8 times 8x minus 1. And now I didn't write out a second step or another step, I guess a third step. I didn't write out another step where I wrote them all over one division bar because I know that, okay, if these are multiplied, I can really just think of this as over a single division bar like that. So I see that the x plus 8 squared on top, two factors of x plus 8, divides out with the two factors of x plus 8 that are in the denominators of the two rational expressions. The 8x minus 1 factor divides out, and I'm left with simply x plus 2 over x minus 8. as um, my simplified form. Any questions on that one? So I would say if you got through this one comfortably and got a really solid start on the next one, you should be pretty, happy with yourself and your ability to do factoring at a reasonable pace. If you made it through the first one and didn't quite make it to the second one, but you basically got to the end, you should probably be, that's good enough. And if you didn't make it through the first one, within the 9 minutes or so, maybe go back and review a bit of factoring. What was it that took the most time here? Was it the, finding your M and N's over here? Was it remembering how to do AC grouping? uh, sometimes it just happens that you go down a path and you make a silly arithmetic error and realize, 4 steps in that, oh, wait, I made an error and have to go back and correct it. And that's just going to happen to everybody once in a while. So if it was something like that, maybe you write that off. But if that's happening all the time on the homeworks, maybe be a little more careful with, the bookkeeping, as I call it, kind of making sure that from one line to the next, everything is copied correctly. Anything that's changed is a valid algebraic operation and so on. But all that being said, if you didn't quite complete this in the 9 minutes or so, that might be something to kind of drill a little bit, working on things like factoring or the algebraic steps to complete this. All right, and then the second one, we have this rational expression 1 times rational expression 2 divided by rational expression 3. Well, we'll start out with just factoring everything. The first numerator, we see a factor of 3x can come out, leaving us with 3x times x plus 8. 3x plus 2 on the bottom is prime. There's nothing that we can factor out of there. It's only a linear, so we can't do any other more interesting factoring methods. The second rational expression, the numerator, we can maybe do guess and check here. We could do AC grouping, that would be fine. But I kind of see this 3x plus 2 here, and I see that I have, I'm going to definitely have one of my factors is going to have a 3x in it, and one of my factors is going to have a 2 in it. And I think to myself, I wonder if 3x plus 2 is a factor of this, right? Again, that little reverse engineering mentality. And indeed, 3x plus 2 times x minus 1 works. I would have to multiply 3x by x to get 3x squared. I'd have to multiply plus 2 by minus 1 to get a minus 2 for my constant term. And I check the cross terms, I get plus 2x minus 3x, and that's out to negative x. Exactly what I was looking for. I don't think it was that hard to even guess and check this one without kind of this little hint of the 3x plus 2, but definitely with it, it made it even more manageable. So that's the numerator. The denominator, I'm looking for two numbers that multiply to negative 30 that add to plus 1. They need to be opposite in sign, so I'm thinking plus 6 and minus 5, or the other way around, minus 6 and plus 5, but plus 6 and minus 5 here gives me the positive coefficient. So x plus 6 times x minus 5 for that denominator. And then lastly, my third rational expression, the denominator x plus 6 is prime, nothing to do with it. But my numerator I know I can factor out a factor of x and at least a factor of 2. If I wanted to, I could come over here and get a prime factorization for both 72 and 84. If I didn't, immediately recognize that both were factors of 12. But I see with my prime factorization, they share a factor of 3 and 2 factors of 2. And 72 is 3 times 2 times 2, or 12, times the 3 times 2 that remain, 6. So 72 is 12 times 6. And 84 is 3 times 2 times 2 times 7, 12 times 7. So I see I can actually factor out 12 as the numerical part, and then the x from the variable bit, so I factor out a 12x times 6x minus 7. Okay, so now that I've got that done, I wasn't worrying about writing out all the restricted values here, but we could. The restricted values, x cannot be, when is this denominator 0? When x is -2/3. This denominator will be 0 if x is -6 or +5. This one, when x is -6, we already got that. But also we're dividing by this entire fraction here. Anytime this entire fraction is 0, we also have a problem, which is when, say, x equals 0, or when 6x minus 7 equals 0. So we have lots of restricted values here. So we could write that out. And then the key here to kind of procedurally to realize is that, well, if I have a bunch of multiplications and divisions strung together, any rational expression that immediately follows a divided by sign, I invert and multiply. Anything that's multiplied together, I just keep them multiplied together. So I invert this one and multiply. And I see that, again, I could take extra time and extra effort and write all of this over one fraction bar. But I know that once I have everything multiplied together, that's basically over one fraction bar already. I can divide out my factors of x plus 6. I can divide out the factors of 3x plus 2. Anything else, the x plus 5 on the bottom doesn't look like it shares any common factors. 6x minus 7, no, x minus 1, x plus 8. But I do actually see a little more that I can work with here. The factor of x all the way out in front and all the way here at the end can divide out. And I also see I've run out of colors, but the 3 can divide out the 3 and the 12, leaving me with just a 4 factor. So after all of that going across the top, I get x plus 8 times x minus 1. That is everything that's left in the numerator. And in the denominator, I have a 4 times x minus 5 times 6x minus 7. And I think that is everything from the denominator. Yep. So again, these were two longer problems. If you got through both of them completely, kudos. That was a lot of work. I kind of didn't expect you to get through both of them completely all the way to the end with the restricted values and everything. If you got through the first one comfortably, I would say that you should be, happy with yourself. You got through the first one and got a pretty good start on the second one. If you didn't quite make it through the first one at all in the whole 9 minutes, maybe revisit the factoring sections, do a little more drilling there, try to speed up that process a little bit. Unless, like I said, if it was just something where you made a silly algebra flub at some point and realized it and had to go back and correct it, that happens sometimes. That takes some time. As long as that's not happening regularly, maybe not something to really worry about. All right, any questions on multiplying and dividing rational expressions? Okay, then let's move into 8.3, adding and subtracting rational expressions with like denominators. And in a later section, next class, we'll talk about how to deal with unlike denominators. If you remember just numerical fractions, when we have like denominators or common denominators, things proceed a lot more easily than if we have different denominators. So again, let's take a look at an example like, say, 1/4 plus 5/4. Just a numerical example, and in some sense, the simplest possible addition of rational expressions, just numerical fractions. Okay. So we might remember that if I have a over b plus c over b, same denominator, then I add the numerators, but I keep the same denominator. I don't get like b plus b or something on the bottom. I keep the same denominator, right? In other words, if I think of, let's think of like pizza. I have a pizza and it's divided into, say, 8 slices. If I have like 2 slices, 2/8, and then like plus one more slice plus 1/8, well, then I have 3 slices of pizza. I have 3/8 of a pizza. The eighths are what determines the slice size. How big is a slice of pizza? That doesn't change if I get more slices of pizza or get fewer slices of pizza. They're still all the same size slice. They're still all 1/8 of the size of a whole pizza. I just either have more slices or fewer slices. So if I accumulate more slices, the slice size doesn't change. That's what we're saying here. I have kind of A slices and C slices of a pizza where the slices are sized according to this denominator B. So I have a total of A plus C slices of that same size. So when I'm adding, or for that matter, subtracting fractions with like denominators, the denominator doesn't change. It's still the same pizza slice size. I just have more pieces, more slices or fewer slices. So I get 1 plus 5 all divided by 4, or I can simplify that to 6/4. And I see that 6 is 2 times 3, 4 is 2 times 2. I divide out my common factor of 2, and I get 3/2. And working with rational expressions is going to be fairly similar. I have 2 rational expressions here that are being subtracted. Whether we're adding or subtracting isn't of a ton of relevance here as far as the procedure goes. But I'll follow kind of similar steps to what I did before. I'll start by simplifying everything. In this case, though, I recognize that I have subtraction and I have like denominators. If I have, say, one numerator that, divides out nicely with one of the factors in one of my denominators, I probably don't want to divide that denominator out because I really like the fact that I have like denominators. So that's maybe the one main difference between the last section and this section is where last section I started by trying to decrease the complexity by simplifying everything that I could before maybe doing the division or multiplication. That became a little less relevant when we weren't so worried about, writing everything over one fraction bar. But I probably don't want to do that here. I really want to maintain these common denominators. Okay, but let me start by trying to factor these out. I know that my denominator factors into x plus 8 times x minus 8 in both cases. Now, one thing that I could look at here, I can look at, say, 7x squared minus x plus 46. And if I factor this, what does that give me? Let's just say, I don't want to think too hard about this, but let's just say it gives me like 7x plus 1, x plus 46 or something like that. It's not what it's going to be, but let's suppose that it was. And let's say something similar with the second one here. Maybe it's 6x plus 1, x minus 10. So if I factor these like this, one thing that could happen is it could divide out with one of the factors of the denominator, but I don't want to do that, right? I want to maintain this like denominator here. Sorry, my lawn guys decided to come a day early, so they're like mowing my lawn outside of my window. So I don't really want to do that. But what am I going to be looking to do? I'm going to be looking to subtract these. So then I have the difference of two factored polynomials. Is that really helpful for me? I think this is also not really helpful for me. So instead of, oh, it won't let me undo anymore. Instead of taking this approach, I do want to note that for my denominator, x cannot be 8 or negative 8. Those are my restricted values. So I factored my denominators, got my restricted values. But I think my numerators, I'm actually just going to leave as they are. And I have what, 6x squared plus 14x minus 10. Now, when I subtract these, what do I end up with? I get 7x squared minus x plus 46. That first numerator minus the second numerator. And then remember, I keep the same denominator at the end here. X plus 8 times x minus 8. Now we could, take a shortcut here and just do like 7x squared minus 6x squared plus x minus 14x. But I think it's good practice to distribute the negative sign or the -1 through. So I have a minus 6x squared minus 14x and then plus 10. And now I identify like terms. I have 7x squared minus 6x squared is 1x squared. I have minus x minus 14x minus 15x, and then plus 46 plus 10 plus 56. Now I'm looking to factor the numerator. I'm looking for two numbers that multiply to positive 56 and then add to negative 15. I note that 56 is 7 times 8, and negative 7 plus negative 8 is negative 15. So I see there are really two places that it benefits me to factor. One is maybe factoring the denominator early, so I can get my restricted values before I do any operations. I think that's usually uh, a good approach. It might be a little bit more writing, but just always getting your restricted values as early as you can in the problem. Just make sure that you don't do anything like, mistakenly divide something out before finding the restricted values. But in this type of problem, adding or subtracting rational expressions, it's really at the very end where we want to simplify that the factoring process is really helpful. Because now we see we can divide out the x minus 8s, and we're left with x minus 7 over x plus 8. Right, factoring up here in the numerators isn't super helpful because number one, we don't want to divide anything out at the beginning because we have like denominators already. So we don't want to divide anything out. And number two, if I have, x plus 1 times x plus 3 minus x plus 2 times x plus 4, well, to simplify this, I actually have to multiply back out, do the subtraction, then try to factor again. So So the procedure for adding or subtracting rational expressions, a little bit different than the previous one. We don't want to simplify at the beginning because we want to keep our common denominator. And we probably don't even want to factor the numerators at all because that's not really going to help us very much. So let's look at an example like this one here. So let's try to simplify 18x over 4x minus 1 plus 6x plus 3 over 1 minus 4x. Now we do see that these are two rational expressions being added together, but they don't have exactly the same denominator. One is 4x minus 1, the other is 1 minus 4x. Why is this in the section with like denominators? Well, these are two different denominators, but they're so similar, they're really easy to make look like one another. I noticed that 1 minus 4x is negative 1 times 4x minus 1. Right, so I could think of this as 18x over 4x minus 1 plus 6x plus 3 over negative 1 times 4x minus 1. It might help me to remember another fraction property, that if I have, let's say, negative 1 times the fraction b over c, that's the same as negative 1 times b over c, which is the same as b over negative 1 times c. Or instead of writing the negative 1, I can write it as negative b over c is equal to negative b divided by c, which is equal to b divided by negative c. But I'm writing it this way because we have this negative 1 factor out here, so it looks a little more familiar. So really, I see that I could take a negative in the denominator. I could pop it in the numerator if I wanted to, or I could pop it all the way out front of the fraction. Now, a little side note, if I had, say, 2 times b over c, that's equal to 2b divided by c. The 2 can pop into the numerator, but that's not equal to b over 2c. So be a little bit careful that it's because this is a negative 1 that I can move it into the denominator or out of the denominator like this. I can't do this with another number like negative 3 or positive 4 or something like that. So, just be a little bit careful there. But effectively, this negative 1 can come all the way out and change this plus to a minus. So I can get the denominator that I want. I can get like denominators pretty easily in this case. Or I end up with 18x minus the entire numerator, 6x plus 3. Make sure to put that in parentheses, over 4x minus 1. I'll distribute the negative just to be careful. Super easy to drop a negative sign here. So 18x minus 6x, and then minus 3. Or that's 12x minus 3 over 4x minus 1. Or this is 3 times 4x minus 1 over 4x minus 1. Or this is just 3. And this, of course, has a restricted value. X cannot be 1/4. Otherwise, 4x minus 1 would be 0. We'd be dividing by 0. So this thing equals 3, but only when x is not 1/4. Okay, 2 exercises to wrap things up today. So we have 2 similar exercises to the previous ones that we saw. The factoring is a little bit more challenging. but still, I think pretty manageable. So one thing to remember is, so up here, we're going to flip the, if I can select it, we're going to flip the denominator, the order of the terms, by pulling out a -1. And then we're going to do subtraction. So don't try to factor 10x squared plus 21x minus 13. And also don't try to factor 3x squared plus 4x minus 1. Right? Get the denominators to be like denominators. Do your addition or subtraction. And then after you've done the addition and subtraction and combined all the like terms and simplified the numerator, then try to factor it and divide out common factors. Down here, we already have the same like denominator. We want to keep that like denominator. You can factor it, or try to factor it right away if you want. That's fine, and get your restricted values right away. Or you can, wait till right before you simplify. It's, it's going to be okay to wait till right before you simplify in this case, but, I like to get the restricted values as soon as possible. So I would factor the denominator early, get the restricted values, and then proceed with the subtraction and simplification from there. Okay, so we'll take about maybe 6 minutes or so for these two, and then come back and discuss. Okay, so it's about 6 minutes. Let's take a look at these two. So the first one, again, we note that the denominators can be made into like denominators by just noticing that 4 minus 7x is -1 times 7x minus 4. And uh, we rewrite the sum as the difference 10x squared plus 21x minus 13 over 7x minus 4 minus 3x squared plus 4x minus 1 over 7x minus 4. We subtract our numerators. So 10x squared plus 21x minus 13 minus the entirety of 3x squared plus 4x minus 1 divided by 7x minus 4. We distribute the negative sign. So we get 10x squared plus 21x minus 13 minus 3x squared minus 4x plus 1. And then we combine together like terms. So in the blue, I circled the x squared terms. 10x squared minus 3x squared is 7x squared. In the green, 21x minus 4x is 17x. And in the red, -13 plus 1, -12, all divided by 7x minus 4. And again, that numerator, I could factor it with AC grouping, but I maybe make an educated guess and say, I wonder if, the only thing that it can reasonably cancel with here is 7x minus 4, which is prime. So I wonder if 7x minus 4 is a factor. And indeed, if 7x minus 4 were a factor, to get 7x squared, I would need a factor. I would need to multiply by x for my firsts. To get minus 12 for the constant, I need to multiply -4 times +3 to get -12. I check my cross terms. The outsides give me plus 21x. The insides give me minus 4x. 21 minus 4 is indeed plus 17. So this does work, right? So making a kind of an educated guess, again, kind of a little test-taking strategy there. Can we reverse engineer something a little bit? It does end up working. And the 7x minus 4 is divided out, giving me x plus 3 as the simplified form. With the restricted value, of course, x cannot be 4/7. That would make 7x minus 4 is 0. So that's our restricted value. And then our next example, 5x over x squared plus 5x plus 6 minus 7x minus 4 over x squared plus 5x plus 6. And here we have already a like denominator. So I combine them. I get the new numerator 5x minus 7x minus 4. And I'll factor the denominator x squared plus 5x plus 6 factors into x plus 3 times x plus 2. I note my restricted values. It's always good to, I think, to do this as early as possible so that you don't risk kind of getting rid of, canceling something or dividing something out and losing a restricted value, or even like putting something else in and gaining a restricted value that's really not there. So these are restricted values. X cannot be -2 or -3. And then we simplify the numerator. We distribute the negative into the 7x minus 4, making 5x minus 7x plus 4. That's -2x plus 4. If we factor in -2 out of there, we get -2 times x minus 2, almost matches that x plus 2, but not quite. So this is our final answer. Note that x minus 2 and x plus 2 do look pretty similar, but there's really nothing that we can do to make them divide out. If I tried to kind of put the negative sign back in, I would have -x plus 2. Now the plus 2 matches, but the x and -x don't match. So x minus 2 and x plus 2, even though they look pretty similar, there's really no way to divide those out. So this is what we have. This is our final simplified form. There's really nothing more that we can do to this. We can't do anything with that x minus 2 and x plus 2 to make them kind of go away in any way. Even though, maybe it kind of sometimes looks like morally they should, but it doesn't quite work out. Any questions on any of this? Okay, so that was our rundown of 8.2 and 8.3. Add, subtract, multiply, and divide. Rational expressions, we'll add and subtract with like denominators. Next time, of course, if you remember from numerical fractions, adding and subtracting with unlike denominators is a bit more complex. So next time we're going to devote our class meeting on Tuesday to adding and subtracting rational expressions with unlike denominators. And then Thursday's class will wrap up chapter 8 with complex rational expressions. And that will wrap up the material for the course. So again, remember Unit 2 exam this week. If you haven't taken it already, do that in the next day or so. Final exam coming up. As always, I will have office hours from 10:30 to 11 today. Otherwise, if I don't see you, have a good weekend, and I will see you on Tuesday. All right, have a good one.